Hi, welcome to Algebra 2 Common Core. We're going to begin Unit 5, which is Sequences, with Lesson Number 1, an introduction to a sequence. So our first definition is, a sequence is an ordered list of numbers. So fill that into your notes. And let's take a look at a couple examples of sequences. The first example that I've shown you, 1, 6, 11, 16, 21, 26. You should notice that there's a pattern to this sequence. Now, not all sequences have patterns, but this one happens to have the pattern. Do you notice it? I can add 5 to get the next terms. So, for example, if my last term that I've written down is 26, my next term is going to be 31, 36, 41, and so on. So we see a pattern to this one. For the second example, 1, 4, 9, 16, 25, we see that this sequence, I think I recognize that one. That's all my perfect square numbers. So the first term is 1 squared, then 2 squared, then 3 squared. So right now I've got 25, which is 5 squared. The next term would be 36, which is 6 squared. Then 49, which is 7 squared, and then 64. So this one has a pattern as well, so that allows me to find the next terms of the sequence. Now, if the sequence comes to an end, then it is called a finite sequence. So a finite sequence contains a finite number of terms. So it stops. However, we also are going to have examples of what we call infinite sequences. So an infinite sequence is going to be one in which there are an infinite number of terms. So there's no stop to that pattern. It just keeps going. Now, when we're looking at each number of a sequence, it's called a term or an element of the sequence. We denote the terms of a sequence in subscripted form. So if I want the first term, I can call it A sub 1. Notice how that 1 is down a little bit lower and smaller number. So the terms of a sequence could be written as A1, A2, A3. If I want what is called the nth term of the sequence, then that just means if I count over n terms, no matter what n is, that's called the A sub n term. The one right after that would be the A sub n plus 1 term. So we're going to get pretty good at looking at these terms of a sequence in subscripted form. Now there's nothing special about the letter A. Terms could also be referred to with a T, so T1, T2, T3, and so on. Continuing on, let me add one before the nth term this time. So the one before the nth term would have a subscript of n minus 1. We're also going to see in this unit that we don't have to use subscripts to stand for our terms. We can also use function notation. So I could say F1, F2, F3, etc. And continuing down that line, the nth term would be F of n. The term that comes after the nth term would be the F of n plus 1 term. And if I want to go a next one, then it'd be the F of n plus 2 term. Now, since domain and range are so important in Algebra 2, we refer to the domain of a sequence as well. And the domain is going to be the term number. So if we've written it in subscripted form, then the domain is going to be that subscript. The range is going to be the terms of the sequence. So basically, those are the outputs for any input, which is the term number. There are two forms that we are going to become familiar with for writing sequences. The first form is called the explicit form. In the explicit form, I'm given a rule for how to find the nth term of a sequence. So in this case, I'm going to be given the rule. My rule will be in terms of the variable n. So I'm going to be given the rule in terms of n. Now again, n is going to stand for which term I'm looking for. So let's look at the first example. I want to find the first three terms of the sequence. I'm given an explicit formula, and I notice that in my formula, an is going to be my nth term, and that's in terms of the variable n. So in the case of a1, what I'm really thinking is that n is equal to 1. So if n is equal to 1, we're going to say 3 times 1 minus 1. 3 times 1 is 3. 3 minus 1 is 2. I'm then going to find a2, which would be the second term of the sequence. So 3 times 2 minus 1, that's giving me an answer of 5. And let's go ahead to the third term. So 3 times 3 minus 1, that's giving me an answer of 8. So the first three terms of this sequence would be the numbers 2, 5, and 8. Now this sequence does keep going, so I'm going to put ... there. And again with the designation that 2 is the first term, 5 is the second term, and 8 is the third term. Now if you look at that sequence closely, you should recognize that that one has a pattern as well. That important pattern is going to be significant in tomorrow's lesson. But we do notice that the pattern is add 3 each time. Let's go to example number 2. Find the 5th term and the 10th term of the sequence. Again, I'm given an explicit formula. So I look at the formula, an, so the nth term is equal to n divided by n minus 1. So that tells me that I don't have to know all the terms ahead of it. I can just find a5 right away. I don't have to find a 1, 2, 3, and 4 if I'm given an explicit formula. So a5 just means that I'm using an n value of 5. So I'm going to put 5 in for n, and I get 5 divided by 5 minus 1. So the 5th term is going to be 5/4. I also want to find the 10th term, so that means that n is equal to 10 right now. Substitute that into the formula that's given to me, the explicit formula, and I have 10 divided by 10 minus 1. So this 10th term is equal to 10/9. I could have given you any term to find, and because I'm given the explicit formula, I can find that term just by substituting my n value. Sometimes our explicit formulas are a little bit more complicated. For this example, I've got an is equal to negative 1 to the nth power times n squared minus 2. So if we want to find the first 4 terms, I'm going to start with n equaling 1. So that means I'm finding a1 by substituting 1 in for n. So negative 1 to the first power times 1 squared minus 2. So that's giving me negative 1 multiplied by the answer negative 1, which is 1. So the first term is 1. Now I'm going to let n equal 2. So a2 will be equal to negative 1 to the second power times 2 squared minus 2. So for this one, be careful. Negative 1 to the second power is positive 1. 2 squared minus 2 is 2. So 1 times 2 gives me an answer of 2. Let's go to term number 3. So n is equal to 3 right now. So a3 will be equal to negative 1 to the third power times 3 squared minus 2. Notice that each time I change n in this formula, I have to adjust my exponent on my negative 1 and also my n squared term. So this is giving me -1 multiplied by 9 minus 2, which is 7. So my third term, -7. For the fourth term, when n is equal to 4, we've got a4 is equal to -1 to the fourth, multiplied by 4 squared minus 2. -1 to any even power is going to give me a +1. 4 squared minus 2, that's 14. So 1 times 14 is 14. So I've got the first 4 terms of the sequence, 1, 2, -7, and 14. Now, sometimes we'll be asked to go the other direction. Here's a sequence. Let's find the explicit formula. Again, notice that we're finding an explicit formula, so we want to know how to get the nth term, an. So let's look at the first sequence and see if we can find the pattern. One pattern that I note is that I can add 4 to the previous term to get the next term. But if I have to talk about the previous term, then that's not going to be conducive to using an explicit formula. We'll see those kinds of examples in the next page when we talk about recursive formula. So instead of thinking of the pattern as add 4 each time, I want to talk about what each term represents. And if we look closely, we see that the first term is 4 times 1. The second term, 4 times 2. The third term, 4 times 3, 4 times 4, 4 times 5. So if n stands for my term number, to find each term, I'm just going to multiply 4 times the term number. So my first term, 4 times 1. My second term, 4 times 2. 4 times 3, and so on. So this was a pretty easy explicit formula to write down. And again, notice that an explicit formula has to be in terms of the variable n. Let's look at part B. 5, then 8, then 11. So I'm noticing that the pattern is add 3. But in each case, I've got to add 3 to the previous term, so that makes it a little bit harder to write my sequence in terms of the one ahead of it. That would be a recursive formula, not an explicit formula. So we've got to think about how I get an explicit formula for this. So I have to come up with a way of writing an. When n is 1, I want the answer to be 5. When n is 2, I want the answer to be 8. When n is 3, I want the answer to be 11. Now, since we notice that we're adding 3 each time, we might think about saying 3 times n is going to be part of my formula. But what am I going to have to do with 3 times n? I'm going to have to add it to 2. So go back and check and say, okay, when n is equal to 1, 3 times 1 plus 2, does that give me 5? Yes. 3 times 2 plus 2, does that give me the next term, which is 8? Yes. 3 times 3 plus 2, does that give me the next term, which is 11? Yes. And so on down the line, I think I have the right explicit formula. Now, later in this unit, we're going to have a way of coming up with this term explicit formula for any sequence that happens to have an add pattern. Let's look at the last example. The last one goes 2, 4, 8, 16. Now again, you might notice that I multiply by 2 to get the next term in the sequence. But I don't want to use that kind of pattern. I instead want to look at each term. So I'm going to say, oh, well, really, these are just the, not multiples of 2, but powers of 2. So I'm going to say 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. So that tells me that my explicit formula should be 2 to the n. Now let's take a look at the other form of writing a sequence. So this is called the recursive formula. The terms of a sequence can also be written using a recursive formula by looking at what the pattern is. So for this one, 12, 24, 36 means that I'm going to take each term and I'm going to get to the next term by adding 12 on. So 24 plus 12 gives me 36, and so on. So a recursive formula looks like the following. I have to be given the first term. In this case, the first term is 12. I also am given a way of getting the next term. So notice how we reference these terms. A sub n stands for the nth term of the sequence. A sub n minus 1, that stands for the previous term, the term that came before the nth term. So this definition basically tells me to find any term in a sequence, I'm going to take the previous term and I'm going to add 12 to it. So you'll notice that a recursive formula must have two parts to it. What are the two parts that we have to have? We have to have a definition of the first term. So I can't do anything unless I first of all know where my starting point is. So I'm always going to have to be given a sub 1. The second thing I have to be given is a formula to find the next terms. Or I might write this as the formula to find the nth term in terms of a previous term. So let's try an example here. Let's say that I give you the sequence -2, -5, -8, -11, and so on. To write a recursive formula, I'm going to say A1, the first term, is equal to -2. To find any term after that, I'm going to say the nth term is equal to the previous term, an minus 1. And what do I have to do to each term? I have to subtract 3. So you'll notice that to find any term, I have to know the one that comes right ahead of it. So let's try using recursive formulas. Write the first 4 terms of the sequence. A1 equals -4, and then an is equal to an minus 1 plus 5. Whenever I'm looking at that subscript, n minus 1, all I'm going to think is the term before. So if I have that A1 is equal to -4, then to find A2, that means that right now n is equal to 2. I'm going to use the formula A2 is equal to A n minus 1. 2 minus 1 is 1 plus 5. So that means that A2 must be equal to the term that I already have, -4 plus 5, and that's equal to 1. Let's go to the next term. To find A3, that means that right now n is equal to 3. So that is going to be equal to A, n minus 1, 3 minus 1 is 2, plus 5. What did we say a minute ago A2 was? A2 is equal to 1, so 1 plus 5 is equal to 6. To get A4, we're going to take A3 and we're going to add on 5. So A4 is just equal to 6 plus 5, which is 11. So this sequence starts with -4, then we've got 1, then 6, then 11, and we should see that this pattern is just add 5. My recursive formula tells me that pattern right there, add 5. Now let's go ahead and try the next one. A1 is equal to 8, so my first term is 8. To find the next term, A2, that means that right now n is equal to 2. So that's going to equal A, look at the subscript, 2 minus 1 is 1, plus 6. So I'm going to substitute 8 in for A1. 8 plus 6 gives me 14 for my second term. To find A3, that means right now n must be equal to 3. So A3 is equal to, look at your subscript, 3 minus 1 is 2. So I'm going to take A2 and I'm going to add 6. Well, a minute ago we just found that A2 was 14, so 14 plus 6 is equal to 20. When I'm finding A4, that means that n is equal to 4. So I'm going to use the subscripted value a to the 4 minus 1, so a to the third, a sub 3 plus 6. But my third term was 20. So 20 plus 6 gives me 26. So the first four terms are 8, then 14, then 20, then 26, etc. Now you'll notice that this one has the pattern of take any previous term and add 6. Let's try a couple more that have a little bit more complicated recursive formulas. A1 is equal to 5, so I'm starting at my starting point of 5. To find the second term, I want n to be 2, so I'm looking for a sub 2. So that's going to equal the previous term. The previous term is A1, so 2 multiplied by the previous term A1 plus 3. We know the previous term is 5. So 2 times 5 is 10. 10 plus 3 is 13. To find A3, that means right now that n is equal to 3. So A3 is going to be equal to 2 times A2 plus 3. So substitute 13 in for A2. 2 times 13 is 26. 26 plus 3 is 29. I have to move over here for A4. That means that n is equal to 4. So A4 will be equal to 2 times A3 plus 3. So A4 is going to be 2 multiplied by that term that we just found, 29, plus 3. 2 times 29 is 58. 58 plus 3 is 61. Now there's another way that we can write our subscripts, and I want to point that out with this next example. We're still given A1, which is equal to 3, so that tells me my first term is equal to 3. Sometimes we write the next term, an plus 1, in terms of the previous term, an. So in this case, I'm going to say if I want to find A2, then really my subscript right here has to be 2. So that tells me that in this situation, n is equal to 1. So I'm going to take my first term, my previous term, and I'm going to square it. So 3 squared, of course, gives me 9. Go to A3, where I'm going to use A2, the previous term, and I'm going to square it. What's the previous term? 9. 9 squared, 81. And for my fourth term, we're going to say a sub 4 means that right now n is equal to 3. So we're going to take the third term. Let me just fix that a little bit here. We're going to take the third term and we're going to square it. I think I need my calculator for that one. So A4 is equal to 81 squared. And on my calculator, I got an answer of 6,561. So this sequence is 3, then 9, then 81, then 6,561, etc. This sequence is getting big very quickly. So let's look at the two different kinds of sequence formulas that we had. For the sequence 2, 4, 6, 8, 10, we can either write the sequence with an explicit formula, where we want our an to be in terms of the variable n, whatever the subscript number is. So A1 is 2, A2 is 4, A3 is 6, Okay, 4 is 8. So you should notice that these are all multiples of 2. So I can write the explicit formula as 2 times n. So 2 times 1 gave us the first term of 2. 2 times 2 gave us the second term of 4. 2 times 3 gave us the third term of 6. 2 times 4 gave us the fourth term of 8. Now, that's an explicit formula. That's all that's required for our explicit formula. I can find any term in the sequence by using that formula. A recursive formula for this one would have to have 2 parts. I've got to write down the first term, a1 is equal to 2. And then to find any next term, we're going to call that next term a sub n. You'll notice that the other thing we can do is just add 2 to get the next term. So how do I write that as a formula? A sub n minus 1, the previous term, plus 2. So you can see that these two formulas look very different even though the sequence is exactly the same sequence. If you have any questions about this, please see me about these two different notations. For our last example, I want to show you that we can also use function notation to find sequences. So I've got f of n. F of n is going to stand for the nth term of the sequence. Now, f of n minus 1 just means the previous term, the one that comes right before the nth term. What does f of n minus 2 mean? It means the term that is 2 ahead of the nth term. So for this sequence, I've already got that f of 1 is equal to 1. And I see that f of 2 is also equal to 1. So if I want to find f of 3, that means that right now n is equal to 3. So in order to find f of 3, using this formula, which happens to be a recursive formula, I'm going to say let's put 3 in for n. So I'm going to say f of 3 minus 1, which would be f of 2, plus f of 3 minus 2, which is f of 1. I'm going to plug 1 in for f of 1 and 1 in for f of 2. So that tells me that f of 3 must be equal to 1 plus 1, which is 2. So far my sequence is 1, 1, 2. Let's find the next term. So if I want f of 4, that means that n must be 4 right now. So f of 4, n stands for 4, so f of 4 minus 1 would be f of 3. F of 4 minus 2 would be f of 2. Plug in those values. F of 3 we just found to be 2. F of 2 we know is 1. So therefore, f of 4 must be equal to 3. So put that right here as the next term in my sequence. I'm going to go at least one more here. F of 5, that means n is 5. So f of 5, when n is 5, I'm adding together f of 4 plus f of 3. F of 4 we just found out was equal to 3. F of 3 we know from above is 2. So the answer for f of 5 is 5. Maybe you're starting to see the pattern that's happening here. Make room for one more term. So if I want to find f of 6, that means that n is equal to 6. So f of 6 will just be equal to f of 5 plus f of 4. Well, f of 5 we just found out was 5. F of 4 was 3. So that tells me when I add them together that f of 6 is equal to 8. So my next term is 8. Maybe you've seen this sequence before. This is called the Fibonacci sequence. Something like this, Fibonacci. Fibonacci was a famous mathematician who noticed that we could add any two terms to get the next term of the sequence. We'll be talking a lot more about sequences in class when you come back, and we'll see you then. Have a great night. Bye-bye.